Ferrari from Buenos Aires. He's going to talk about soliton decomposition of the box ball system.
Okay. Thank you very much for the invitation. It's great to be in Rio again, at IMPA, in this impressive colloquium with all these students. We are sharing now rooms sometimes. So I thank you all also for coming here. So some people here listen to this talk, but it is changing title and contents, but not the model. This is a joint work first with Leonardo Rolla, Chi Nguyen, and Min Wang from Buenos Aires, and Davide Gabriele de L'Aquila, from L'Aquila. Okay, so here you have a system, so you have to think about an infinite sequence of zeros and ones, and this is a deterministic dynamics. So I will call eta the configuration of zeros and ones. I put the ones in red only for you to see better. And then theta is at time 1 would be. And the thing is the following. This is a transport system. So there is a carrier that is coming from minus infinity that picks balls. The balls are the ones that are sitting in boxes, that the boxes are the integers, and picks balls. Each time it visits boxes one at a time from left to right, and then each time that it finds a ball, it picks up, and if it finds an empty place, it deposits the ball in the empty place. Okay, so here is easy. Here at this time he picked up this ball, and then here it was empty, so he put it, and so in next time it will be in this place. Okay. Then he picked these two balls. So here he had one ball. Then after these two, you have two balls, and deposit these two balls here. Here the carrier arrives, it has no balls, so this will be empty, this place. So here he picks three balls, deposit one here because it's empty, then picks another one, so he has three balls here, and deposit these three here. Okay, it's clear the dynamics. Okay, here I call X the integers. The configuration is a subset of Z. That is the subset occupied by 1. So you can think this is a function from Z to 0, 1. And eta of X will be 0 when it's empty. Eta of X is 1 when there is a ball at X. And here I have a simulation of the same thing there. With in the middle line, I put how many balls has the carrier at each time. Okay, this system is the totally deterministic system. Okay, it's just a dynamical system. You go from one configuration to the next one in a deterministic manner. This is a system that was invented or introduced by two Japanese researchers, Takahashi and Satsuma, in the 90s. And then it stayed in Japan all this time, until 2 years ago that a Russian living in Madrid called Zuk went to Japan and did a work with two Japanese, collaboration work with two Japanese, but they say from a mathematical point of view. These are physicists, so all these things are in the physics literature. And then recently, this year, we were starting working on that when Zuk came to Buenos Aires and gave a colloquium. We said, interesting problem, let's see what's going on about here. So we were working on that. We didn't write the paper yet, so it's in preparation. But then a couple of months ago, Levin and collaborators, I will give the reference later, published another mathematical work. So in some sense, it is infiltrating to the west from the east, long east, far east. Okay, so this system, the motivation of Takahashi Satsuma was to give a simple version of the KdV equation. the Grice equation. That is u dot equal to third derivative plus u prime. This is totally solvable, this equation, and they have solitons that I will tell you soliton what is, but that are traveling waves that they collide, change maybe a bit locally the speed, but then they continue at the same speed after collision and with the same shape. So you have to think that here you have space and here is time, okay? I picked this picture from the internet. In fact, there is no mathematical relation between KDB and BBS, but you will see that the behavior of this BBS system is very similar to this one. So in this paper, Toshihiro Takahashi, Matsukadaira, Satsuma, and Junkichi, and then Takahashi and Matsukadaira, they have a lot of relation between here is KDB and here is the BBS. And you don't need to read it, but you can go to the paper and see the computations. But really, there is no mathematical relation in it. So the two papers, mathematical papers, are one is this ZAG. They consider a version of the process in a finite box. And Levin, Liu, and Pike, they consider a semi-infinite box, but with a number n of particles that is increasing, and compute things that are, in some sense, orthogonal to what we are doing. So you will see. In particular, all these people worked with finite number of balls, because for infinite number of balls, you see that you have a problem that you don't know the carrier how many balls it had when it started at minus infinity and how much he spent in the way, okay? So, in fact, it's not possible to define the process for any infinite configuration. Or you can invent ways to do it. You can say, well, okay, I define it in finite place and then truncate the configuration and then go on. But it's not useful doing like that. So I will tell you an easy way to define it and to define also the set of configurations where you can define the process. So I will use this usual walk representation of the ball configuration. So if you have configuration that have zeros and ones, I changed my picture. I forgot my zeros and ones here. I will put, so suppose that you have zeros and one here. I will put a down segment for each zero and up segment for each one, okay? So and this will give you a walk, and you will say that if you have the origin here, at the origin the walk has height 0, because if not, you cannot localize it, okay? So suppose that you have zeros, these are zeros, these are ones, these are zeros, these are ones, and these are zeros, okay? And we will say that x is a down record, so I will call psi of x the height of this walk at site x, that it will, x now it will work as time for the walk. It's a record if it is a record in the sense it's a down record. That means that eta of x is less than xc of x is less than xc of y for each y to the left. So you're coming like that. So your walk are coming like that, and these are all records, okay? If you have well, I am a bit tendencies here because I am telling that you are going down. No, but let me take infinitely many balls here, and then suppose that I am able to say that x is a record. That is possible because I can explore all the configuration to the left. This tells you immediately that to define that X is a record is not a local function. If you change the configuration to the left far away, then you can change as you want to have or not have a record. But if X is a record, then I define the configuration at site X like 1 minus eta of X when X is not a record. Okay, so these are, I put in black the records and in violet the non-records, and then the blackened records. So if the configuration is finite, it's very easy because you will have records. You will have a line of zeros, and then at some point you start with your balls that are going up here and then down, up and down, and then they will finish. So this will be an excursion of your walk, okay? And so the configuration is just to flip down the excursion, okay? So I just put this a little bit down, but the new configuration, this will be t eta, and this will be eta. The new configuration is just flip down the excursion, okay? Okay, so, but for this to be, so with this I define, this is well defined for all configurations, in fact. If you have no records, then you just flip the whole configuration, okay? That there will be, for instance, the case when you have a random walk, if you have a random walk with probability 1/2, symmetric random walk, okay? Because you will have no record for that trajectory. You just flip the whole trajectory. Okay, the carrier load then will be like in Q in theory, will be the height of at site X for configuration eta will be the height at X minus the height of the minimum. So in the pictures, what you are doing is you keep the excursions and flat the records. Okay, so from this configuration, you just put this flat here and keep the excursions. Okay. Okay, so you have bijections between bulk configurations, walk representation, and carrier load representation. So I will use indistinguishably one or the other. Okay, now I define a configuration with density lambda are the configurations that if you compute the proportion of particles in a box of size n to the right or to the left and take the limit, when n goes to infinity, you get lambda. Okay, so you have lambda. So lambda, and then have that if lambda is less than 1/2, I take bigger than 0, then x lambda is closed for t. So if you start with a configuration with more balls, but with a density that is less than 1/2, and you apply your operator, you will have density less than 1/2 for t eta. Okay. Okay, I am interested in sets that are closed for the dynamics because I am looking for invariant measures for that operator. Okay, so I will consider the set X will be the set of all configurations that have a definite density less than 1/2. And then I have this T induces operators on the space of function and on the space of measures. Okay, so I say that the measure is invariant for T if the measure after one step is the same as the measure at time 0. Okay. So the first exercise, in some sense, is show that if you have IID Bernoulli lambda, this is invariant for T. This is for all lambda between 0 and 1/2. For this, you don't need to do anything because your random walk, so the carrier load is a random walk that is going up with, so now you think that X is time, and then the carrier load is a random walk that goes up with probability lambda. When it finds a ball, it goes up, and then goes down with probability 1 minus lambda if you have, if X is bigger than 0, so from 1 to 0. But from 0 to 0 is when the carrier is empty, you stay with probability 1 minus lambda. If with probability lambda, you go up. Okay, so this is just a stationary random walk for lambda less than 1/2, reflected at the origin. So the geometric distribution with lambda divided 1 minus lambda is reversible. So the carrier load trajectory of eta has the same law as the carrier load trajectory of the reflected of eta with respect to 0, if you reflect the trajectory like that. And then from that, you can conclude, because I will have that this violet thing here are the balls in eta, okay? But the balls in eta, by reversibility, have the same distribution that the balls in the reflected of eta. The balls in the reflected of eta, when you come here, you will see the ups hills here. So the distribution of these violet things is the same as the distribution of the red things, but seen from left to right, okay? From the right to the left. Okay, so now I want to prove the balls in theta are Bernoulli, okay? So this will be, the balls in theta are exactly the places where you deposit the balls that were the up jumps in, are the down jumps in eta. So you see the down jumps in eta are the balls in theta, okay, these red things. But the down jumps in eta have the same law as the down jumps in the reflected of eta because of reflection. But these are the same as the reflected up jumps in eta, but these have distribution reflected IID because the jumps in eta were IID, but the reflected IID are IID Bernoulli, so we have proven the theorem. So in fact, this thing, you don't need to do anything, just basic probability. So at this point, I am already in page 12, but I will give you the theorem in page, I don't know, 30 maybe. So you start to be anxious. What are you doing? And so here is a list of desires. So the first thing, we will get the ball configuration, an eta, and we'll make a decomposition in solitons. A soliton, this I take from the regular dictionary, is a solitary wave that propagates with little loss of energy, forget about that, and retains its shape and speed after colliding with another wave, such wave. That is the picture we saw in KDV. Okay, so I will show that this dynamics has solitons, and I will give you a very precise decomposition in those solitons. And then I will show that the evolution is a hierarchical translation of these components. That you just will translate the components, but in a very particular way that is hierarchical. The big guys translate first, say. And then we'll show that the measures that have independent soliton components are invariant for T. And then I will give you an explicit soliton decomposition for IID Bernoulli measures. Okay? So these are the goals, so you have to be patient and grasp some definitions, because I have to do this decomposition and it's not totally immediate. First of all, let me motivate you about that the solitons are conserved. So I will call a k-pod a set of k1s followed by k0. So here we have a 3-pod, and here another 3-pod, okay? And now I do the evolution here. So the empty carrier comes here, picks these 3 balls, and puts them here, okay? So the next step, I will have these 3 1s followed by these 3 zeros. So a 3-pod, it translates by 3 unities at each step. So a 1 million pod translates by 1 million units for a step. So the length of the wave, that you can think that are these 3, is the speed of the object. And the distance between two 3 pods is conserved. Here is obviously conserved, okay? But it is conserved also when there are some interaction. I put here just an interaction with a 3 pod with 1 pod. So the 3 pod is coming fast at the speed 3, the 1 pod is coming slow at the speed 1, and then collide at some point. You say, well, at that point they destroyed themselves, but not. They just collide, they mix a little bit, you don't know who is who. And after a while, the 3 pods emerges at speed 3, and the 1 pod emerges at the speed 1. All of this is just the dynamics of the carrier that is picking the ball. I only add the colors here, and I had 2 kinds of colors for the K-pods and no colors for the other zeros, because all ones are in some K-pod, but not all zeros in some K-pod. So I have 2 kinds of zeros, the zeros that are part of excursion, part of the K-pod, and the zeros that are records. So let me denote the zeros records by dots. So you here have a much nicer picture, and here a much nicer. So here you have 2 pods and 1 pods that are interacting here, and they have some distances here that are conserved and are the same here, and the distance between the 1 pods here are the same here, okay? So the idea here is that you will have many different kinds of objects, and you would like to identify even when they are in the middle of the mess here. Okay, so let me use this Takahashi-Satsuma soliton identification. This is from their paper. So suppose that you have a finite number of runs, and this is the configuration we saw at the beginning, and then some finite number of balls, and then I define run as these lines, okay? This is a run of zeros, then a run of 1, run of zeros, run of 1, etc. Just this is a maximal segment of identical contents. And we explore the runs from left to right, and we look at each run and the next one, and if it is the previous one is smaller than the next one, then you use the K boxes of the first run and the first K boxes of the second run and call this a K pod. In this case, the first time that you have that is when this is less or equal than this, okay? So you will have these 3 zeros and these 3 ones as a 3 pod, and I put it red, okay? A very simple algorithm. And then you do the following. You ignore this already identified K-pod, put all these things here, so you will have a run here that continues here, okay? And then the next run will have 4 guys here plus 1, 5, that is shorter than this one, that is infinity, so you will have a 5 pod that uses these 4 guys here, 1 guy here, and these 5 down segments there. Okay, you have, then I have identified one 3 pod and 1 5 pod, and then you iterate that. You now ignore these 2 guys and go to the and explore again. Okay, in this way I can identify the K-pods in any finite configuration. All ones will belong to some K-pod, and then I call the head the set of 1, so the head of this blue 5 pod is this one and this one. The head of the red are this one, and the tail are the zeros. Okay, so the tail of the K-pod of the 5 is that one, and the tail of the red is that one. For infinite configurations, you can use you see that in the excursion, when you finish the excursion here, you eliminate all these guys, and you will have an infinite set of an infinite sequence here. So you can treat the next excursion as if it was empty to the left. So you can just do this algorithm excursion by excursion with no pain. Okay? An excursion will be a configuration between two successive records. Okay, now I have the following proposition, that this k-pod conservation under T, that this says that eta, the configuration eta, that is this one, has a k-pod gamma with tail T gamma, if and only if T eta, that is this configuration here, has a k-pod gamma prima with the head at the same place of the tail. So the head of this red one, that is this one, goes to the tail, goes to its tail, that is this one, okay? The head of this pod goes to its tail, okay? That is coming here, okay? And the head of that one goes to its tail, that is this one, okay? Goes here. So this k-pod, I can identify the same k-pod in the configuration eta and the configuration theta. Here you have a bigger picture. So you have this big pod is coming here. They are separated, but this is coming fast, so it's eating them. And finally, he leaves and leaves the other people far away. So the big ones pass by, and the small ones stay backwards. And here you have a carrier version. I put this because it's almost the same as we saw in the picture for the KDV. So it's just to. Okay, now it's an important point here is that you need to look, if you want to find things, you need to look at the process from the point of view of a record, not from a point of view of the origin, for many reasons that will be clear later. So so a record is just, in this picture, is just any of these black things, okay, or here. The black things is a record. So I just take a record 0, say, and look from the height of record 0. See, here I have a nice picture to see it. Okay, so you have, suppose that this is height 0. So the origin maybe is here, okay? And the record at height 0 will be this one. So R0, eta 0 is this one. And then when you evolve, the record comes here, and then you evolve, the record comes here, and you evolve, the record comes here, okay? And you are looking from this place, okay? At each time. That's here. So I will call RT eta I the position of the ith record that corresponds to height minus I. And I will look at the system as seen from the target record, and I will put a hat for saying that I am doing this translation. Okay, now I will call slots. That the slots, you see that in our first picture we have this 5-pod here. We have a 5-pod, but then the 5-pod have a 3-pod here. This is a 5-pod, and this is a 3-pod, this one, right? So in some sense, what I did was I have it here, and I inserted this 3-pod in this point. And I could insert it in several points, but I cannot insert it at site 2 because I will destroy the 5-pod. But I can insert it in these two positions. Okay, in these two positions or in these two positions. So this is what I am saying here. This is really important for the decomposition. So the potential slots, so supposing that an M-pod has the origin at 0, so the potential slots start at 1, at I, So to the left, these two, these three. For the 5 pod, there are 4, and 4. There are 4 in the head and 4 in the tail. Okay, but the k slots I can put only in hk plus 1, hm, tk plus 1, tm. So this you can play with that if you want to insert the k pod and keep alive the 5 pod. You cannot insert anyway, but you have two m minus k places to put it. Okay. Okay. So here I have an example of what. Well, here the definition of what means insert the k pod. This put the k pod here and then translate the rest of the configuration to the right. So I am inserting the k pod and the boxes also, not only the balls and the zeros, but I insert the boxes and push the rest of the configuration to the right. Okay. And here are the different positions that I can put 3 pod. So it's 2 times 5 minus 3. There are 4 possible positions, 2 in the head and 2 in the tail. Okay, now I will do the following. I will get a configuration, make the k-pod decomposition using the Takahashi-Satsuma algorithm between 2 records. So I will do this in between 2 records. So I have the record 0 and have the record -1, that is the height 0 here. Okay, and then do this picture. Okay, for this picture, you do the following. Pick the biggest guy here. The biggest record, the biggest k-pod here is a 6. Okay, this one. And then say that there is a 6 slot, so I will construct a slot for all k. I have a k slot at the records -1. I put this in between records 0 and -1. The distance here do not mean anything. It's just a way to put things in a readable way. Okay, so I attach a 6 pod at record -1 because here is where it is attached. In general, the biggest k-pod will start here at the slot at the record. Okay. Okay, and then this 6 pod produces 2 5 slots. Okay, 2 5 slots. And I look if there are 5 pods, and yes, there is a 5 pod. That this is violet here. That is at some spot, at some slot. That is the second slot of 6 pods. So I put it here. Okay. So I attach the 5 pod here. Okay. Now I go to level 4. The 6 pod produces a new slot for 4. The 5 pod produces 1 also here, and then here is the same for the tail, and this slot goes down all the way, and this is the new slot created by the 6 pod, and here is the same. This goes, but then I have to sum the 2 slots produced by the 5 pod, okay, and so on. At this point, you have to believe me that it's that, and here let me stay. So what I am doing is just take 2 records, look at the maximum k-pod present between the 2 records, start with m, append the m at a slot corresponding slot, and then iterate. Set the L-1 slot like the L slot I had before, plus 2 new slots created by the pods, the K pods, the L pods I put there, and then attach. No, then go back, append, and so on. Okay, this is what I did here. Okay, now I do the following. I have this configuration. So for each k, I have slots that are these dots black dots and red dots. This is a tagged one slot. And I have attached one pods here, okay? So I have a configuration here that contains only one pod. I will put a 1 here at this slot that is -17, and a 1 at this slot that is -7. And this will this part of the configuration will have all zeros here, a 1 here, a 1 here, and zeros in the rest. Okay? And then the same for 2. Well, 2 and 3 are empty, but 4 has a 4 pod at -5. So for each line, I construct the configuration of monopod. There are only one kind, but I can have more than one guy. I could have 2 one-pods in a row in the same place, okay? So from eta, I constructed mk of eta, that is the configuration of k pods of eta in the k slots. And mk eta of I is the number of k pods in the ith slot. In the example is that. Okay, and I can invert that. If you give me those configurations, I can do essentially the same procedure and construct this tree, and from this tree construct this configuration, and this configuration, forget about the colors and this one. So I can go from the k-pod decomposition that is this mk back and forward. Now, I want to see how do the components evolve with the dynamics. So for that, I compute the number of the flux of m-pods. I look at the number of m-pods that are to the left of record 0 in eta, minus the number that of m-pods to the right of record 0 in t eta. No, minus, no. And here, sorry. Here, where you see minus star, you should see and. It's almost the same. So this is the flux of pods of k-pods of m-pods between the two things, and then the position of the 0 slot will be exactly this flux, no? Because okay, you will see. So the position of the 0 slot we'll see for each m-pod that crossed the 0 record, I carry 2 m minus k slots. Okay, so the position of the k slots when you count from the 0 record has been translated by 2 m minus k and this flux. And see that this is for m bigger than k. So see that the 0 slot displacement is a function of the 0 k slot displacement is a function of the m pods for m bigger than k. Okay, here the soliton appears. So this theorem is important. It says that the k-pod component of t hat eta, so the process as seen from the target record, is a shift of the k-pod component of eta. And this shift is the shift given by the shift of the slot, so theta is the shift given by the shift of the slot, plus kt, that is the original dynamics that the k-pods want to do when they are empty. So in the slots, they behave like if there were nobody else, and the other guys work like an environment, but does not change. That changes only the speed of this and locally the shape, but not the configuration. So eta is conserved. So each of the components of eta is conserved. At time t, you have just a translation of each. So it's a hierarchical translation because you have this translation depends on the eta, on the the components bigger than k. So here I am remembering which are the things. So at this point, we can call this soliton because are isolated waves that do not change speed or shape after collisions. Okay. So I will show in an example how this happens. So this is a configuration, it's a ball configuration. This is a k-pod decomposition, the k-pod identification, and this is the evolution of this configuration. Okay, and then you will get this. This was the tree before the evolution, and this is the tree after the evolution. And then you can check here that this is exactly what I tell you. So here you have the displacement of the k slots, and you see that the k-pod displacement with respect to the k slot is just k. Okay. Okay. So let me say again what we have proven is that if you take a configuration eta, apply the dynamics as seen from the target record, and make the k-pod decomposition is the same as make a translation of the k-pod decomposition at time 0. This theta is this thing. So this is just a reminder. So what we proved with Rolla, Wang, and Nguyen is that if you have independent components, then and translation invariant, independent components, then the law of the configuration that is coming from these independent components is invariant for the dynamics. Okay, I have no time to show it, but it's only the proof is very easy and uses that the two things, that this thing is that the evolution is a translation, and that this translation is independent of the configuration, of this configuration. Okay, I jumped here, and I want to show you a couple of results that we did with David De Gabriele that I like a lot, because so you have a IID Bernoulli with parameter lambda, and then you define lambda k by lambda 1 is lambda 1 minus lambda is the probability to see an isolated one pod, and then you have a kind of complicated recursive formula for lambda k. So you have lambda 1 to the k and this product of a previous thing, and then the theorem says that if you have that eta x, so eta is Bernoulli, IID Bernoulli lambda, then the components are a product of coordinates, and in each coordinate you have a geometric with parameter 1 minus lambda k. And lambda k is defined here. And that the components are independent. So this would be a proof that Bernoulli is invariant for the dynamics, but a bit more complicated than the one I gave you before. But the advantage is that you can generalize that and create a family of measures, but just giving weight. So you have a family of alphas, and the sum of the alphas is less than infinity. And then weight omega of xi. So xi is an excursion. The weight omega of xi is just alpha k to the number of k pods you have in the excursion. Okay, that is xi. Okay. And then you have a lambda k that is an iterative formula in function of alpha that you can compute explicitly. And then you take new alpha, you take independent versions of this measure. So these weights induce, under this condition, induce a measure on the excursions. Okay? And then you took a product measure of this measure on escutcheons, and nicely comes out that the components are IID geometrics with this lambda k and independent. In particular, you can put this alpha to get an easy model with a magnetic field, so that the density of ones, suppose that the -1 you put 0, so that the density of ones is less than 1, so the Ising model will be also of this shape and will be invariant for the dynamics. Okay? Well, I think I finished here because my time is over, no? Or do I have time? No. Or maybe I have 3 minutes. Well, I have to go back because in some other talk, and there's some people that was here in the previous talk, I was claiming that if I had a record mixing or ergodic invariant measure, then the measure should be product of components, but we couldn't prove that yet. So it's here now as a conjecture. And I finish here. Thank you.
Thanks.